All right, Algebra 1B students, welcome to part 2 of lesson 7.7. Today we're going to talk about exponential decay, and we're going to begin on page 462. But before we get there, just as a reminder, when we have this exponential equation, y equals a times b to the x power, that's an exponential equation. Remember that our initial amount is our letter A, and our growth factor is a letter B. Okay, those were our vocabulary terms from the previous video. Initial amount is A, growth factor is B. And remember that when we talk about growth factor as a percentage, it's always 1 plus whatever our rate is as a decimal, right? So if our rate is, for example, 4% or 0.04, then we do 1 plus 0.04 as our B value. All right? Now that is in reference to exponential growth, like we've been looking at the past couple days. Today, we're going to look at exponential decay. And a couple key things are going to change in exponential decay. All right, and the first thing is our B value. Our B value is what decides if we have exponential growth or exponential decay. Okay? When B is bigger than 1, it's 1 plus something extra, adding something on, we are growing. When our B value is less than 1, but still a positive number, then we are getting smaller and smaller every time, right, as we go forward in our x values. So our B value needs to be between 0 and 1. So it could be things like 0.5, 0.4, 0.3, something like that, or even 0.8, anything like that. Decimal between 0 and 1. And now we're going to call that our decay factor. Okay, that's called the decay factor because it's telling us how much we are decaying every time. Okay, every time that we go forward 1 in our x value. The A is still the initial amount. That does not change. Still the initial amount. And now our base, or our B, is called the decay factor, which we can see right down there. All right. So we're going to look at an example problem where we're going to model exponential decay, and that is really all we need to worry about tonight, so it should be a relatively short video. So let's look then at this problem here. Another word problem, another science problem, where they're asking us to model this exponential decay. All right, and what the problem says is the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. That's going to be important. 101. For every 1,000 meters we go up in altitude, the pressure goes down 11.5%. What is the approximate pressure at an altitude of 3,000? Okay. So the first thing we need to do is try to write an equation, an exponential function that will model this situation. So we should always go back to our exponential model, our exponential formula, and decide what is my initial value and what is my, in this case, decay factor, because we are decreasing. Okay, that means decay. That should be your first clue. Decay, decreasing. Right? So our x value, which we're going to leave as a variable, is the altitude in thousands of meters. So for example, when we begin, our first rise is going to be 1,000 meters. We will put 1 in for the x value. Okay? Y is going to be the atmospheric pressure. Our A value is the initial pressure. When our altitude is 0, that means sea level. Okay? Altitude is 0 at sea level. Our initial amount is 101 kilopascals. So that's going to be our A vector. All right, and then our decay factor, and this is where things change a little bit. Notice, please, that our 11.5% is rewritten as a decimal, 0.115. And now instead of doing 1 plus our decimal, like we did in exponential growth, we are doing 1 minus our percent. And it should make sense why it's minus, but you're going to answer that question for me in a little bit. But hopefully you can see why we are subtracting away this percent. So our decay factor is now a number between 0 and 1 because we started with our whole thing and we took away 11.5%. We decreased 11.5%, which means our decay factor is right here, 0.885. Right? That's my B value, or my decay factor. Okay, so I'm going to rewrite my equation. Instead of A, I'm going to have 101. And instead of B, I'm going to have 0.885. So here's my exponential equation. Y equals 101 times 0.885 to the x power. Right? That's my exponential equation. From there, all I need to do to answer this question is decide what is the atmospheric pressure at 3,000 meters. Now remember that our x number, which was altitude, is already in thousands of meters. So at 3,000 meters, our x value should be 3, because it's 3,000 meters. Okay? So instead of my x value here, I'm going to put in a 3, substitute 3 in for x, and on our calculator we do 0.885 to the third power, multiply that answer times 101, and we get right about 70. So it's about 70 kilopascals at an altitude of 3,000 meters. All right? That is all I'm going to ask you to do in your practice problem set. So hopefully that makes sense to you. If it doesn't, go back and rewatch or make a note to ask me in class tomorrow. What I would like you to do is the got it number 3, which you should find right there in the middle of page 463. Page 463 of your book. I just want you to tell me the atmospheric pressure at an altitude of 5,000 meters in the previous problem. It should be less than the answer we just got. It should be less than 70. And then in part B, tell me why do we subtract the percent decrease from 1 to find the decay factor. Answer those 2 questions and you will be all set for your practice problem set. That's all for tonight. Hopefully you have a great night and I will see you tomorrow.